Recording. All right, so we are recording. All right. Well, so I'm assuming that we are all kind of keeping up with the reading and following up, the concept discussions and whatnot in this class. So we are now continuing with the discussion of propositional logic. All right. So I have an example here. Okay, this is really for today. So I'm just gonna put in, 0, 1, P, Q, R, S, T, and then we have phi, rho, and also in theta. There we go. And here we go. All right. So this is Joplin, in case you haven't noticed. Joplin is an app for taking notes. On one side, I am using Markdown for the most part, but all the equations are entered using LaTeX. On the other side, it is rendered, so it's kind of nice. So what we are doing here, okay, is I'm just going back to the whole concept alpha, which are the symbols that we use, in propositional logic. And then in this case, I'm keeping omega simple. So omega is really just going to be the typical operators that we have, which includes negation. It includes conjunction, okay, which is a wedge. It includes disjunction, the or, and we'll just throw in your right arrow, which is implication. All right. So now we have alpha, omega, iota, and also zeta. Okay, so we'll go through these one by one. Alpha is defining all the symbols. Okay, basically we have constants, 0 and 1 are constants. P, Q, R, S, T are variables, so that means that they can be true, they can be false. We don't know exactly which one is true, which one is false. We just know that they're variables, Boolean variables. And then we have the three Greek letters. They are called schematas. So look at those as wildcards for pattern matching. If you know what I'm talking about, like regular expression, that's a good experience to have, in terms of wildcards. If you don't, that's okay. If you have ever used the command line interface and you say, I want to look at all the bitmap files, okay, asterisk dot png, the asterisk is a wildcard, okay? It is a placeholder to go like, okay, I'm looking for this particular pattern here, okay? Anything that fits the pattern, show me on the command line. And I truly feel sorry for people who have only used GUI on their computers. All right. So that's what the schematas are for, but I will talk about what schematas are, how they're utilized later on. And then in terms of operators, which are also called connectives, it is represented by omega. So in this case, omega consists of negation, it has conjunction, it has disjunction, it also has implication. And then we have iota. So iota is basically a set of well-formed formulae that are known or given to be true. So we say, okay, the negation of false is known to be true. We say the true is known to be true. And then we throw in something like this, like P and Q is known to be true. Q implies R is known to be true. And then we finally have not S implies not R is also known to be true. And that is all we know about this entire propositional logic system to begin with. And then we have zeta. Okay, so zeta in this case is way simplified because we also explore that for human propositional logic derivation, zeta tends to have like 20 something rules. Okay, so I'm just only using a few because I just want to illustrate how do we make use of the rules in zeta. And you can see that zeta is the only time when the Greek letters appear. Essentially, we're looking at a pattern. Every transformation rule is like this. Okay, so let me just kind of make a separate point here. So each rule is like, oops, this. So I'm just gonna use this symbol here. Let me finish, and then I will talk about what that means. Okay, we'll just throw row here. All right. So when we look at a single rule in Zeta, it has a set T on the left-hand side of the symbol that looks like a rotated T. That means infers. Okay, so that's inference. So in this case, we have set T infers, and I'm just picking one of the three Greek letters as an example. I just pick rho, okay, but you can also use theta or you can use phi, okay. Any one of the three that we have listed here, we can put those here. I typically use psi, and also not theta. So let me just kind of change this a little bit. It doesn't really matter, for this particular discussion, but just to be consistent, I like, that that's just, what I usually use, but it's not really important here. All right. So a rule looks like this. It has a set of t on one side, the infer symbol in between, and then we have rho, on the other side. So rho is really just a well-formed formula. Okay, so I probably should not use rho, but some kind of well-formed formula. So I'm gonna use, WFF here, WFF, some kind of well-formed formula. So the way it works is T as a set specifies a pattern. Each element of T consists of um, the Greek letters combined with some operators. Okay, so T can also be empty. Okay, if I want, I can also make T empty. So let me give you a rule that in which T is empty. So I'm going to put it at the beginning of this zeta here. So we have an empty set, and then we say infers. Okay, which is V dash as a symbol. And I'm just going to pick a Greek letter. We'll just use phi in this case, and then we'll say this or the negation of phi. So this rule, which I just typed in, right now, is a transformation rule in which it says, oh, I don't need anything to be known. Okay, the empty set says, in terms of pattern matching, I don't need anything at all. And I can come to the conclusion that any well-formed formula phi or the negation of itself is going to be marked as known to be true. Does that make sense to you? So the way this works is you're looking for a specific pattern that is on the left-hand side, that's specified by the left-hand side of the infer symbol. Whatever pattern you find, okay, we find all of these things to be true according to this pattern. And then what you do is you say, okay, there's a well-formed formula using the very same Greek symbols, and that is known to be true. You can mark it as known to be true. Okay, so that sounds kind of abstract. So that's why, I have this example here, and we're going to try this out today. We can even use WFF, and we can use it as an expression that is parameterized using the three Greek letters. Okay, so we have phi, we have rho, oops, and then we have psi over here. So whether all three are going to be used or not, we don't care. Okay, we can have one that is not used at all. Okay. All right. So what we'll do is now we will come to we'll talk about the set D. If you have read the reading material, you know what D is representing. If you don't, that's okay. I'm going to explain it at least a little bit. Okay. But if you have read the notes ahead of time, it really helps to kind of make the connections, in the class. So we are referring to the added notes here since 2022. So what we want to do is to consider a set W. Okay, so we'll kind of shift gear a little bit and talk about what W is representing. So what do you think W is representing? You can always read the rest of the sentence, but what is it representing? What is this notation here? It is a set, right? In which for each element beta, beta is a well-formed formula. In other words, W is really the set of all well-formed formulae. Are we good so far? With respect to our alpha and our omega. Does everybody understand what I meant when I said with respect to alpha and omega? No. Okay. So alpha defines all the constants and the variables. So I can choose to only have three variables like PQR without the SNT. So if I only choose PQR to be the variables, then the um, well-formed formulae would be limited to only use those three variables. Does that make sense? On the other hand, if I expand and say, okay, we are going to use PQRST, now we have five variables, then the amount or the kind of well-formed formulae that we can come up with would also be different. Does that make sense? Okay. So the other thing is we can also change the composition of omega. There's no need to put in implication because A implies B is really the same thing as not A or B. So that means implication is really redundant. It really is not needed. Okay. It is nice to look at, but it's not really needed. So if I change the composition of or the elements in omega, that would also affect what is going to be in W as well-formed formulae. Does that make sense? So in other words, when I said W is the set of all well-formed formulae with respect to A, alpha, and omega, it really just means that W, which is the set of all well-formed formulae, is quote unquote a function of alpha and omega. That's basically what it means. Are we good so far? All right. There is a dependency. Okay. There's a dependency of what can be in W based on what is in alpha and also what is omega. Okay, that I think that is probably the plainest way to explain this. Are we getting that concept? Yep. Mm-hmm. Mm-hmm. Beta. Mm-hmm. So this is W is always with respect to a particular alpha and a particular omega. Yeah, exactly. Yep. Yep. We can define alpha and omega differently depending on what we want to do. Okay. So in other words, W is the set of all well-formed. Let me kind of point to where I'm pointing at, where I'm looking at. W is the set of all well-formed formulae with respect to alpha and omega in consideration. That's basically just what I said. I'm actually shocked at the consistency of the way I speak. It's scary to me that I can basically say exactly the same thing as what I have written here in 2022. All right. So iota is a subset of W because iota is the set of all well-formed formulae that are given to be true or that are known to be true. Don't ask me why, we just know they're true. Is that okay? Can everybody relate iota to W? W is everything that is syntactically correct. I is everything that is known to be true to begin with. Okay? Are we good? All right. So now we are going to define D, okay? So D is also a subset of W, so that D is a set of well-formed formulae that are derivable from the well-formed formulae in iota, and in this case, it will be using zeta. In other words, if I know, everything in iota to be true, what else can I also infer to be true? So everything that can be inferred to be true would be in the set D. Are we okay with that concept? Hmm? Yes, that's the rotation. Yep. It means, there are some prerequisites that you have to satisfy. And then if the prerequisites are satisfied, then we can say syntactically we can derive a well-formed formulae or formular in this case because it's singular to be true as well. So I will illustrate that. I will basically apply, the rule in the zeta that we just came up with, and then illustrate how to apply a rule in zeta. But that's a good question. So we'll make sure that we address that question eventually. All right. So the rest is basically saying the same thing as the what we have in here. So what we'll do is we're going to go back to Joplin. So we'll go ahead and first we'll take a look at what is in W. Okay, so we'll go ahead and say, okay, based on this, what do we think is in W? So in this case, because P, Q, R, S, T are the variables, so that means we can now say, oh, P by itself is an element of W. Okay, is that okay? I mean, let me just kind of make sure that we put a focus here. Are we good with that statement? Okay, so what else is in W? There are a lot of stuff in W, but particularly useless would be P, and P is also in W, right? We can also say that P or not P is in W, okay? Just because P is in alpha and everything in alpha by default is also well formed, and then if we use the operators correctly, then that would also be well formed. So now let's go ahead and take a look at something that is not in alpha, okay, or in W. So we can now say it is not the case, negation, and we'll just pick a variable that is not PKRST. So we can say U, okay? So the letter U is not in W with respect to the alpha and the omega that we have been using. Because in this case, alpha does not include U as a variable, so U, by itself, seen as an expression, is not an element of W because W is representing the set of all well-formed formulae. So I mean, U by itself is not well-formed because U itself is not in alpha to begin with. So are we doing okay so far with that concept? Because it's always good to point out what is in, but also what is not in W, what is not considered to be well-formed. Are we good so far? Yes. hmm Yeah, because I'm negating it. Yep. Yep. So this statement itself is true. Yep. Yep. Some people use a cross, like a line across the element of. I just use the more elemental operators to mean the same thing. hmm All right. Well, so in that case, can someone also understand why not zero is, or everything in iota are also in W? Let's look at each one by one until we are sick and tired. Okay, look at this one. Why is this one in W? Okay, zero is in alpha, and negation is in omega, and it's a unary operator, so that's why not zero is in W. Okay. Now, just because something is in W does not automatically make it in iota. Iota is what is giving the meaning to the propositional system. It is basically telling you what is known to be true. But at this point, we just want to know that is everything in this iota also in W, whether it's well formed or not. So let's look at P and Q. Why is it well formed? Because P is in alpha, Q is in alpha. So both of those individually are well formed. So when we put two well-formed formulae and connect them using a operator that has two operands, in this case conjunction, then the resulting expression is also well-formed. So as a result, P and Q is also well-formed. Now, just because it's well-formed mean in W does not mean that it has to be in iota. So this iota is formed in a particular way just because that's the meaning of that system that I want to derive things out of. So are we doing okay so far? Okay. So now what we want to do is to take a look at zeta and say, okay, if zeta is defined this way, then what else is in the set D? In other words, everything that is derivable to be true is in set D. So automatically, okay, iota itself is a subset of D because those are given to be true. Okay, you have a derivation step of 0. Okay, but they are true to begin with. Is that okay? So now we want to see how we apply these rules. Okay, we'll pick one particular one, and that would be the easy one. We'll pick this one. Okay, so we're gonna pick rho and phi implies rho, infers, sorry, infers, which is not the same thing as implies. It is related, but not exactly the same thing. So we're gonna pick on this particular one. Okay, so we'll pick on this particular production or transformation rule, and then we go like, okay, but what does that mean? Okay, so we'll look at the left-hand side first, the left-hand side of the infer symbol, which is always going to be a set. So with a set, it has elements, right? So we look at each and every single element, and we ask, can we find a conjunction um, that is known to be true or derived to be true at this point? You look at iota, you go like, oh yeah, we have P and Q. So that means if you use substitution, okay, if you substitute rho with P and you substitute phi with Q, then we have a match. Are we good so far? So let me say that one more time. You need to use substitution in order to say that, hey, if I substitute rho with P and we substitute phi with Q, then we have a match of something that is currently known to be true. It can be from iota. It can also be derived later on. So we have a match. Is that the only thing we have to match? Yes. This particular set has one single element, so that's the only match I need to make. So what are we going to do once we have a match? Okay, so we look at the right hand side of the infer, and it says, oh, okay, now we can mark rho to be true by itself. Can someone remind me how did we do the substitution? Rho was substituted with P. So that means, oh, we can now say that P is also known to be true. So let me just kind of write that part, at the end of this whole thing. So we'll go back here. Okay, so we'll say, this is step one. So the way we do step one is we pick a rule from Zeta. Okay, so I will make this super duper clear. So we say, rho and phi is the only thing in the set, and then we have v dash rho itself. Okay, okay, I'm gonna put. So this whole thing is an element in Zeta. Okay, is that okay? Are we are we all agreeing that as strange as this may look like an element, it is an element in Zeta because it's listed there. Okay. So next we do a substitution. Okay. So we now say, substitute. Okay. And the substitution is going to be something like this. Okay. We want to substitute rho with P. So I'm going to use a slash to separate the thing it is substituted with. So this is one substitution. And then the other one is to look at phi. And then we say, oh, okay, we can use Q to substitute phi. So with this substitution, the right-hand side set is matched. Okay, so I'm going to pause right here just to make sure that we understand what it means. Is that okay? Or I should say the right-hand side matches, um, in this case, P and Q, which is in um, iota to begin with. And bad grammar right there. There we go. Okay, so we'll just kind of pause right here and just make sure that we understand everything up to this point. We have a specific rule in Zeta. It says we have placeholders. The placeholders are rho and phi in this particular case. We're not using the third Greek letter. It is okay. It's okay to use only one or two instead of all three. But what this pattern is trying to say inside the set is saying, I'm just looking for a conjunction. That's all I'm looking for. Okay. Can the conjunction have the same thing on both sides? Yeah, rho and phi can match exactly the same thing. I'm just looking for a conjunction. Okay. I call the left hand side rho, I call the right hand side phi. That's what I'm looking for. I'm looking for a conjunction that is known to be true or somehow derived to be true at this point. Can I have a match? So we look at everything that is known to be true or derived to be true at this point, and we go like, oh yeah, yeah, we can find this in iota, because inside iota we have this expression which is exactly p and q, right? So when we look at p and q, and then we look at rho and phi, we go like, can we do a substitution so they match? Oh yeah, totally, right? It's pretty easy. We just have to say, okay, we replace rho with p, we replace phi with q, then we have a match of something that is known to be true. Is that okay? Now, because the entire iota is known to be in D to begin with, so I can now say, let's generalize this a little bit. Instead of using iota, I'm just going to use the set D, which is the set of all well-formed formula that is either known to be true or is derivable to be true. Are we doing okay so far? Okay, because iota is a subset of D, so anything that is in iota is automatically in D by definition. Is that okay? Okay, so now that we have a match, oh, what are we going to do with this? So the infer is really just saying that now we can also claim the following, which is looking at the right hand side of the inference, which is just rho itself. So now we can say, oh, whatever that rho turns out to be, whatever we substitute rho with, which is just your p, that is going to be in D as well. That is the conclusion. So let's just kind of take a step back and make sure that we understand point one at this point. Are we all good with number one, step one? Any questions? No questions? Okay. If you need more time to ask questions, to formulate your question, I'm totally good with that. I can withstand a substantial amount of awkward silence. So we're all good? Okay, I see a few nods. All right. Well, it is being recorded. Yes. Okay. So just wanted to double check because sometimes I say it's being recorded and I look and go like, oh, it's not getting recorded, but it is getting recorded today. All right. So what else can we do? Okay. So let's go ahead and just do a copy and paste here because we have a different rule that says oh, we can also imply that we infer the phi is true. So you can see how it's only one change of the Greek letter. This is the left-hand side of the conjunction. This is the right-hand side of the conjunction. And we can see that, oh, yeah, yeah, we can see that rule is actually also specified in zeta. So that means in this case, the conclusion is just off by a little bit because now we can say, we can now claim that Q by itself is also in D. Are we okay with this one? All right. So because of these two steps, we have now confirmed not only everything in iota are in D, but we also have just confirmed that, oh, guess what? P as a well-formed formula is also in D. Q as a well-formed formula is also in D. In other words, we're establishing more membership in D. Now, D does not expand, okay? D is a set that is just a set already. Okay, it is predetermined, but we are discovering what is in D at this point, step by step. Is that concept okay? We are not adding anything in D. We're only confirming what is in D. There's a big difference between those two. All right. So we're going to move on. Okay, so now we can say, okay, what else can we do? Okay, now that we know everything is in iota are in D, and then we have two additional things that we just established. They're also members of D. So what else can we do? Well, let's take a look here. I think the implication can be useful here. So look at this particular rule. Okay, so let me just type it first, and then we'll go ahead and talk about it. So this time, the set that we are talking about is row by itself. Then we have row implies phi. That is in the set. Okay, both of those are in the set. And if that set is satisfied, then we infer that phi is going to be known to be true. So this rule is, oops, okay, this is in zeta. Okay, so we'll just stick with this for now. Can we all agree that this statement is true? Look at how zeta is defined, right? So you just scan, this is one element, this is one element, this is one element. Ah, okay, this is one element here. So this is exactly the same thing. So we can now establish and go like, yep, that's an element in zeta. Is that okay? All right. So now this time it is a little bit more interesting because the set is no longer just consisting of one single element. It is now consisting of two elements, right? Because if you look at the set here, it has row by itself. It also has row implies phi as an element. Is that okay? It has two elements. So now we are looking for substitution again. Okay, we're basically saying, can we do any type of substitution of things that are known to be in D so that both of these requirements are satisfied at the same time? But row has to mean exactly the same thing. Okay, it has to be consistent. Phi, on the other hand, it has a little bit more flexibility because we are not binding phi to anything that's specific. But row by itself has to be true, and then row implies phi also has to be true. Can we do this substitution so that we can satisfy both of these requirements? Well, let's see. Okay, there are a few implications here. So there's one implication, which is Q implies R. Okay, so that by itself would be, we can do the substitution of Q is row and then R is phi. Okay, that's fine. But now I need to ask, is Q also true by itself? Is Q confirmed to be in D? Just look a little bit up here. Haha. All right. So that means, okay, so let's go ahead and type this. Okay, I'm going to type. So now we want to do the substitution. Substitute. Okay, this is our substitution. We are going to substitute row with oh, Q. We are going to substitute phi with R. Okay. Yeah, I know when I'm typing, it's harder for you guys to read it, but now that I'm done, I'll be good. Okay, I'm doing this little substitution here and say, hey, if we replace row with Q and we replace phi with R, can we find both of those well-formed formulae in D? That is the question. Okay, so let's go ahead and check it out. All right. So that means we are looking for Q implies R. So we look at I, okay, we start with I first, okay, or iota, and go like, oh, okay, yeah, Q implies R is in fact an element of iota. That's given to us. And then we say, okay, but what about rho or Q by itself? So you look into iota and go like, iota does not confirm that Q by itself is known to be true. Oh, what are we going to do? Wait, we in step two, we established the membership that Q is in D. So the idea is we just need to make sure everything is in D. So that means, now let me just kind of make a more or less a summary here. Okay, so we can now confirm that Q is in D, and we also want to confirm that Q implies Q right arrow R is also in D. So now fire the rule, and now we can now confirm. So what are we going to confirm this time? We confirm that phi is also in D, but what is phi? Phi is actually R. So now we just confirm that R by itself as a well-formed formula is also an element of D. Is that okay? So step three is a little bit more involved compared to step one and two, because step three requires that, okay, we have to match an implication, but at the same time, we also need to make sure that the left-hand side of the implication is also a well-formed formula that is in D by itself. So that is the syntactical part of the matching. Is the Greek letters, each one is representing a well-formed formula. And we are looking for the patterns specified by the left-hand side of the inference and go like, can we make this happen with some kind of substitution? And well, turns out we can. Okay. And as a result of matching the set on the left hand side of the inference, now we can say, oh, whatever is inferring is also going to be an element of D. In other words, it is derivable to be true. Are we good so far? Okay. So we are basically marking more and more well formed formulae to be true. Okay, we only start off with the things in iota because those are given, but now we are step by step, okay, circling, go like, hey, this is also derivable to be true, but because of that is derivable to be true, we can use it in more, transformation and so on. So now we can go on a little bit more. Okay, so the next rule is, yes, we are discovering that R is an element of D. It is true, yes. Hmm. Hmm. Because of the rule matching here, because of this particular rule. So the infer, see this phi over here, this phi and this phi must be the same. So that means if we can make this match happen, if we can find an implication where the left hand side is known to be true to begin with, or either known or derived to be true, and we know the implication itself is also known or derived to be true, then we can also confirm whatever is the right-hand side, which by itself has to be a well-formed formula. We know that whatever is on the right-hand side of the implication is also going to be in set D. And the important part is set D is the set of all well-formed formulae that are either known to be true or derived to be true. Are we doing okay so far? Okay. So what else can we do about this whole thing? Well, we have this rule here that we do not seem to have used yet. Okay, so let's try that one. So we'll go ahead and try that one. Okay, so that rule is the negation of phi implies the negation of rho. That's one well-formed formula. And then rho by itself is another well-formed formula. If we can find a match like that, then we can say, oh, we can now confirm that phi by itself is also going to be in D. So now we say this is in zeta. Okay, so I'll just do it really step by step. Can we establish that this statement is true? Okay, we're good because it just matches the last element in the list of the set of zeta. Okay, I intentionally make this zeta deal really small. Okay, just so that it's easy for us to see all the elements and kind of go like, yep, we can confirm that. So now the next question is, can we find an implication where the left hand side is the negation of some expression, the right hand side is also the negation of some kind of expression? So we go like, yep, yep, we can certainly make that match. Okay, so how do we make that match? What substitution do we need? So we now say, okay, let's go ahead and do some substitutions. Yep. This is phi, this is rho. This whole thing is an element. From here, it means, okay, so from the perspective of syntax, okay, it means the last operation is an implication. The left-hand side of the implication has to be the negation of something. The right-hand side also has to be the negation of something. So the comma, this is a set of patterns. That's all it is. It is a set of patterns that we need to match. So the first thing we need to match is, can we find something in D that is an implication where the left-hand side is the negation of something and the right-hand side is also the negation of something. So we look at all the things in D, which starts with all the thing in iota first, so we can find that in iota by itself. It is a subset of well-formed formulae, and those are known to be true. And don't ask me why they're known to be true. It is because it defines the meaning of the system. Yep. So are we good? So mentally, we are trying to make a match here and go like, hey, this is an implication. On the left-hand side is the negation of something. On the right-hand side is also the negation of something. So we have some hope, okay, to do this substitution. So in the substitution, then we go like, okay, so let's see if we can do this substitution. We are now looking at phi and say, can if we replace phi with s and we replace rho with R, would we make a match? Actually, we forgot to use a slash here. So we would make a match for the first element listed in the set, right? But that's not the only thing we need because now we say, okay, now that we know what we want rho to be in order to match this expression, can we find R by itself also to be true? So we first look at iota because that's where we start everything, and we go like, R is not here. R is not one of the elements of iota. Okay, so now we have to look at everything else that are confirmed to be elements of D. P is in D, it's not helping us. Q is in D, that is not helping us. Aha, R is in D, that helps. So now we can say with this particular substitution, we can now confirm that, okay, fire the rule. Okay, so we say fire the rule, confirm. In this case, we are now confirming the rho by itself, but because of the substitution of R is used to substitute rho to make the matching happen. So now we can say whatever is substituting rho, which is, no, I take it back. Whatever is substituting phi, because phi is on the right hand side of infer. So now whatever is substituting phi, which is S, is also to be known, is derivable to be true, which puts it into the set of D. It is an element of D. Is that okay? Are we good so far in terms of how we apply the rules specified in setup? It really is just syntactical matching. Okay, we're looking at the structure of certain types of statements. So this one has a lot of constraints, right? Because we're looking for an implication, but not only does it have to be an implication, the left-hand side has to be the negation of something. The right-hand side also has to be the negation of something. So we are specifying a structure that we're looking for. Okay, once we make a match to the first element of the set, whichever one you want to choose, then we have to say, okay, assuming that we make these substitutions, can we also find rho by itself to be in D? We need that too. But in this case, yes, okay, because if rho is really taking the place of R, then we can say, is R in D? Yep, R is in fact indeed in the previous step. So now we have satisfied all the requirements specified by the set on the left-hand side of the inference. So we quote unquote fire the rule. When you fire the rule, all that means is, oh, okay, look at the right-hand side. Now, in all of these cases, the right-hand side is really simple. It consists of just one of the Greek letters, but it doesn't have to be. Okay, it can be like phi and not rho. I mean, it doesn't make sense in this case, but it can be an expression only involving the Greek letter as components of those expressions. But in all of these cases, they are simple. Are we good so far? All right. So this is a very small example of starting with alpha, omega, and iota defined in the ways that we specified over here, and then going through these rules, and also zeta specified as this, and then going through all the rules, at step 4, we have now confirmed that P has to be true, Q has to be true, R has to be true, and also S also has to be true, only because of everything that we put into iota to begin with. So I'm going to pause a little bit just to make sure that we understand the context of how everything relates to each other. Yes, yes, we can. Yeah. So okay, to use number 3, okay, if you use rho to be not s, and then you use phi as not r, now you have locked down the value of rho. In other words, can we show that not s is true? And we cannot. So that means we cannot fire this rule using that specific substitution. Correct. Yep. Mm-hmm. Yep. Yep. So are we doing okay so far? Yes, go ahead. Oh, the order does not really matter because all we are really trying to do is to find things that we can find elements of zeta that can fire. And the flexibility that we have is the substitution. So you can substitute the Greek letters with well-formed formulae any way you want. It doesn't that's okay. Okay, any well-formed formula can become rho. Any well-formed formula can become phi. The question is with that substitution, plugging it back into the elements of the left-hand side of the infer, can you find all of those in D? If the answer is yes, then you can fire the rule. If the answer is no, then you cannot fire that rule. Are we still doing okay so far? Because we are looking at the interaction of all the different sets at this point. So I'm gonna go take a step back, okay, and kind of reiterate, what I mean by that. Alpha and omega together is going to span the set of W. In other words, what we know as well-formed is dependent only on alpha and omega. Now, just because it's syntactically correct does not mean anything. It just means that it is syntactically correct. Okay, this is a well-formed formula. Iota is basically saying I am a subset of W. Everything in iota also has to be well-formed, but these are known to be true. Okay, so that means don't derive anything. You don't have to derive. These are given to you. These are true to begin with. All right. So the magic comes from zeta, because zeta is a set of transformation rules, otherwise known as productions. So each one or each element of zeta consists of a transformation rule. A transformation rule has two parts. The left-hand side is a set, the right-hand side is a well-formed formula involving the Greek symbols, okay, that may or even may not be on the left-hand side. The left-hand side is specifying, syntactical rules to basically say, okay, if you can find some substitution of the Greek letters with well-formed formulae such that all of these things, okay, each one is known to be in D, okay, the set D, then you can go ahead and fire the rule. So now the question is, what exactly is the set D? The set D is essentially the set of all the well-formed formulae that is either known to be true to begin with or can be derived to be true using the transformations. Is that okay? Are we doing okay so far with these 4 steps? As the result of these 4 steps, we have now established that P is true, Q is true, R is true, and then S is also true. But there is no way we can say that T is also true. Now, T is a variable here, okay, which means T can be true or false. But nothing in iota and also in zeta can ever tell me that T is true or not. It is simply not derivable. So let's go ahead and see what else we can do with this particular set. In particular, particularly, we are looking at the first rule that is listed in the set. Now you note that the way I said it, okay? I said the first rule that is listed in the set, which is not the same thing as the first rule of the set, because elements in a set are not ordered. But when I list elements in a set, I have to use some kind of ordering. So just because it is listed in that order does not mean there's an implicit ordering among elements of a set. All right. All right. So let's go for one more derivation that is utterly useless. Okay. So this one is saying, okay, from an empty set, I can infer, pick any well-formed formula. Okay. Let's call that rho. Okay. And if you OR that with the negation of itself, then we also that that will basically um, yeah, so that's the rule. Okay, the rule is there's no requirement whatsoever. Substitute rho with whatever well-formed formula that you fancy, and then we can now say, oh, okay, the right-hand side is also known to be true now. So we'll go ahead and pick some well-formed formula that is not even in iota, and it is not in D at all. Okay, we'll pick T. Okay, T is one of those things where you go like, why is T even here in alpha? Because we don't use it ever. Okay, fine. So we now say, let's do some substitution here. Rho is now substituted with T. Okay, then you go like, but Jack, there's no requirement that we are specifying here on the left-hand side of the inference. It is an empty set. It specifies I don't need any specific rule. Okay, that's all what it's saying. So that means, oh, T just needs to be well formed. It doesn't even need to be true. It doesn't have to be known to be true. Doesn't have to be derived to be true. It just has to be well formed. Is T well formed in this case? It is. And why is it well formed? It is in alpha, exactly. Everything in alpha is by default well formed. So we go like, okay, the substitution is legit. Okay. So now the question is, with this substitution, have we met all the requirements on the left-hand side of the inference? Yes, because the inference says we don't have any requirements. There are no constraints whatsoever. So we can fire the rule. Okay, so we'll go ahead and fire the rule. Fire the rule. So after we fire the rule, now what can we confirm to be in D? So now we can confirm that T or not T is in the set D. Does that make sense to you? Sure. Because whatever T is, okay, T is a variable, it's either true or false, right? So one of these two, T itself or the negation of T, has to be true. Does that make sense to you? So that means the disjunction between these two also has to be true. I don't even need to care what T is. Okay, so is that okay? So we can confirm certain elements or the existence of certain elements in D that is really not helping us at all. Now, is it semantically sound, which means, does it match the logic that we understand about disjunction and negation and stuff like that? Yes. But is it really helpful in proving anything? The answer is no. Are we doing okay so far with? all of these steps here, the 5 steps that we have performed so far. Okay, so you can probably tell that in this case, even in a simple example like this, W is a set of an infinite number of elements. I can derive an infinite number of well-formed formulae just based on this particular alpha and omega. We can also derive an infinite number of elements in D. So D is also having an infinite number of elements. So if I want you to prove whether T is 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 reachable or provable or derivable or not, when are you going to stop? You cannot, okay? Because you cannot confirm T, but just because you cannot confirm T is in D does not mean that it is not in D. So now you have a problem because remember the needle in a haystack analogy. I want you to find the needle. I'm not even telling you whether the needle is supposed to be in a haystack or not, and the haystack is infinitely large. So you can never tell whether you have not found the needle, but the needle is somewhere, or the needle is not even there to begin with. You cannot differentiate between those two cases. Are we doing okay so far with the analogy and also the kind of raw mechanism of how the transformation rules are utilized? Okay, so the key concept that we are introducing in this lesson is the concept of substitution. Okay, so substitution is the key of how we utilize the transformation rules. Are we good so far? Okay, it might take you some time to absorb this, okay, which is okay. This is also why you have the 2 hours outside of each hour of lecture time that you're supposed to spend to absorb the material and to read the material. That may not be a statement that is really important at a community college level, but once you transfer to a 4-year university, I would say bump that 2 hours up to 2 hours and a half or even three for upper division classes. This is a lower division class at a 4-year university. And I know I'm not a really good professor, but there are even less effective professors at UCs and CSUs. Just be warned. Because I want to make sure that you guys understand that just because you pay a lot more money does not mean that you get a better education. You can always come back to me and say, but Tech, what you said is wrong. I got this terrific bunch of professors at this particular UC or CSU. I'll be very happy to hear that. All right, so let's move on and talk about something else that is related at some point to what we are just talking about. So now we're going to move on to something that does not seem to relate to what we are talking about. So I have some examples here. We're going to skip completeness and soundness for the time being, and we'll skip to resolution. Okay, so resolution is this. Okay, if you want to ask me what exactly is resolution, this is resolution. Okay, so let's go ahead and take a look at just this part here without all the proofs. So what this means is um, phi or psi and not psi or rho implies phi or rho. Okay, so the question is, um, looks like a random Boolean expression here, right? How do we know this expression is always true? How do we know this implication is always true? The most important part is if the left-hand side is true, how do I confirm that the right-hand side has to be true? So you can use a truth table, but you can also use Boolean algebra. So I'm going to explain it using the Boolean algebra, which is this is a good exercise to introduce Boolean algebra because you're going to need it for some other things that we're going to do. All right. So the first step is what am I doing in the first step here? Why can I say that the left-hand side of the equality is the same as the right-hand side of the equality? What did I use to make that happen? It has to do with A implies B is the same thing as not A or B. Okay, so I look at the entire left-hand side of the implication and I say, let's just negate that part and then or the right-hand side of the implication. That was discussed on in the first day of the entire semester. Okay, so what about from here to here? So this one is called De Morgan's Law, and we'll actually talk more about De Morgan's Law. But if I want to explain what is De Morgan's Law, this is what it looks like. So De Morgan's Law, there are actually two of those. Okay, so the first one is to say, I'm going to use A, B, C as variables here. So we will say, the negation of A and B is really the same thing as not A or not B. Okay, so just look at let me scroll up a little bit so you guys can all see the expression. Okay, there we go. So the negation of A and B is the same thing as not A or not B. Okay, so when you look at this, you can approach it in from different perspectives. One is just semantically, does it make sense to you? Okay, it is not the case that A and B is true, means that at least one of not A or not B has to be true. Does that make sense to you? Okay, so you can look at the semantic or the language perspective and say, oh, this makes sense to me already. Great. What if it doesn't make sense to you? Use a truth table. Okay, so you can use a truth table where you have four rows, right? A can be true or false, B can also be true or false, and then you have to show that on all four rows, the value of the negation of A and B as a whole is really the same thing as the value of not A by itself or not B by itself. Okay, so you can use a truth table to prove that. So that's one of the De Morgan's laws. There are two. So the second one is kind of the same thing, except we just flip the or and the and. So that's the other part of De Morgan's law. It says, the negation of A or B as a whole is really the same thing as not A by itself and not B by itself. Does that make sense to you? Okay, so once again, you can look at it from the perspective of, yeah, it makes sense just from the language perspective. Or if that is not the case, you are not convinced, then you can look at this from the perspective of, okay, I'm going to make a truth table to show that these two expressions are always going to be the same, no matter what the values of A and B are. So if you're not convinced from the language perspective, I do recommend you to use a truth table so they can prove to yourself, okay, and convince yourself that, oh, okay, De Morgan's law looks a little weird, but it does work. So the way I look at De Morgan's law is I see it as quote unquote distribution. It is the distribution of negation. But in the process, you have to flip the operator. So that's how I see it. Doesn't mean that you have to see it the same way. I just find it to be handy to look at De Morgan's law from that perspective. All right. So then now we know De Morgan's law. Okay, we go back to this proof here. From here to here, it is the application of De Morgan's law because we have a negation of an and. So after we apply De Morgan's law, we negate each individual component of the original conjunction, but then we have to change to use a or to connect the negated individual components. Are we good? All right. So from here to here, what are we doing? Oh, this is just another level of application of De Morgan's law because we have a negation of an or here. So instead of looking at it as a negation of the disjunction of something, I negate every component inside the disjunction, but then I use a conjunction to connect the negated components. So this is also the application of De Morgan's law. From here to here, we are using the identity of operations. In other words, I can look at phi and go like, okay, phi is a variable, it can be true or false. But if you just say and true, it doesn't change the meaning at all. Now, how can you convince yourself that in a conjunction, true is the identity. In other words, how can you convince yourself that phi, whatever phi is the same as phi and true? You'll be sick and tired of this particular term. A truth table. Use a truth table. You can convince yourself that phi is really the same thing as phi and true. Okay, so it's kind of like x in a regular class. X is a number, right? Numerical value versus x times one. It's the same thing because one is the identity of conjunction, but also the identity of multiplication. So conjunction and multiplication actually share a lot of attributes from the algebra perspective. So I do the same thing with row, okay? So from here to here, okay, the true, okay, this true here is re-expressed as psi or not psi. Now, why do I use the psi? Well, that's because later on it becomes useful. So that's a expansion of true to an expression that has a disjunction where one side of the disjunction and the other side of the disjunction are negations of each other. So from here to here is distribution. Okay, so you can look at the and as a multiplication. You can look at or as an addition. So now we can do the distribution, and then from here to here is this is factoring. So that means what that means is I have not phi and not psi. We also have phi and not psi. By putting these two and using factoring, I can now end up with this, which is the reverse of distribution. And then from here to here is, I can look at not phi or phi as true. I can also look at rho or not rho as true. So we simplify this disjunction into just true. We simplify this disjunction also just to be true. And then we simplify again because true and whatever is just whatever. Whatever and true is just whatever. And now we look at these two and go like, hey, we have phi, whatever psi is, and whatever psi is, not psi or psi has to be true. So we have true here because of these two. And then true or whatever is just going to be true. And so this is the actual Boolean algebra way of proving this implication is always true. It is algebra, but in a kind of weird way because it is Boolean algebra. So now the question is, okay, Tech, I don't think this is going to matter to me because I want to be a programmer or a software engineer. This is Boolean algebra. This is what math people do. As a programmer or a software engineer, I don't have to worry about any of this. Okay, at the at the risk of making this sound like a pun, which it was not intended, is that statement true? Do you need to understand Boolean algebra to become an effective software engineer or a developer? Okay, so why? Okay, 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 that's okay. So you have some kind of condition to express, right? And knowing Boolean algebra can help you express it in an effective manner. Okay, but some people do not care about efficiency. They just go like, okay, I know it can be simplified, but I'm just going to use this really long way and tedious way to express the same thing. So who cares, right? I can just use whatever expression I want. The answer is yes, you can. In fact, use whatever expression you want. Go ahead. Say again. Okay, and why is that? That is true, but it's not just about efficiency because guess what you're going to do as an entry level software engineer or developer? What do you think you're going to do? Do you think you're going to work on a brand new project? You'll be writing new code and doing all the cool stuff. Nope. You'll be doing the equivalence of cleaning the bathroom with a toothbrush. You'll be on tech support. You'll be the first line person who will be given the bug reports, and your only job is to verify the bugs in the bug report. Okay, so that means if you they will assign you to fix a bug, making sure the source code is all backed up, obviously in the repository of some kind, and give you your own branch so you can mess things up and nobody else will be affected by your mistakes. That is your first job. So how do you fix a bug? What is a bug? Okay, a bug most of the time, okay, is the program making a wrong decision. Okay, there's a conditional statement of some kind, and you're going to the wrong branch, or there's a condition for loop, and you're exiting too early or too late. All of those relate to Boolean expressions. Yes. Oh, okay. So they all go back to Boolean expressions. Did you write those Boolean expressions that you're trying to debug? No. Somebody else wrote those expressions, but you need to understand the equivalency, okay? Oh, so this expression is really just meaning this, but that is actually incorrect. And then you have to find out what is the correct way to express that condition. That is why Boolean algebra is actually really important if you want to become an effective software engineer or a developer. It is really important because you need to read the code of somebody else or the code that you wrote last week. Because I cannot tell you how many times I'm trying to read my own code from a few days ago and go like, who would write code like this? You go like, oh yeah, that was myself. And that really kind of tells you the importance of commenting as well, but that's a separate topic. All right. So now we look at this thing here and go like, okay, that is kind of cool. Now, why is that cool? It is cool because on the left-hand side of the implication, we have three things. On the right-hand side of the implication, we only have two things. So that means every time we apply resolution, we are getting rid of something. If it is applicable, we're getting rid of something. Is that okay? All right. So now I'm going to write a transformation rule, okay, using Joplin. So now I go like, okay, what about this? How about we add this particular rule to zeta? Okay, so we add this rule to zeta. So that rule is basically saying, hey, if you can find um, row or phi, and you can find not phi, or we need the third one now, which is psi. Okay, if you can find these two, then we can say, oh, okay, go ahead and infer a new well-formed formula, which only involves rho or psi in it. In other words, phi disappears entirely when this is all done. Okay, there we go. Okay, so we are adding this new element to zeta. Okay, so this element in zeta basically is saying I'm looking for two disjunctions. In one disjunction, it has some kind of a phi. In the other disjunction, the only requirement, the only restriction is we need to have the negation of the same phi that we found in the first disjunction. If we can find two disjunctions like this, okay, then we can fire the rule, and then we make a new well-formed formula. I should say, we can now discover that this particular well-formed formula, which is a disjunction only involving rho, and psi, is going to be in the set D. Now, why is this really cool? Because every time you apply this transformation, we are reducing the number of things. Every time it fires, we're getting rid of something because the phi and the negation of phi, they quote unquote cancel out. It just disappears. Is that okay? All right. You look at this and go like, well, it is really kind of cool because it looks like if we can make everything expressed as disjunctions, then this may be the only rule that we need. Okay, let me say that one more time to and make it more specific. If we can express every Boolean thing, okay, every Boolean expression as disjunctions, and basically there's an implicit conjunction here because both of these have to be in in D in order for the rule to apply. So we are looking at a conjunction of disjunctions. If every expression, Boolean expression, can be expressed as a gigantic conjunction where each part of the conjunction by itself is a disjunction, then this may be the only rule that we need in propositional logic. So that's where we are heading right now is we are basically saying those rules that we looked at earlier, okay, these rules in this particular zeta, that's stupid. That's for people. Okay. Instead, we're gonna say, ah, we're gonna make a new zeta that only has one single rule, and this is it. Okay. But it hinges on one really important thing. Can we really re-express every Boolean expression as a conjunction of disjunctions? That really is a big question, right? Can we actually do that? So in terms of the notes, because I really want you guys to read this ahead of me, ahead of the class. So we are now going into the CNF, part of this entire discussion. So we need to look into what exactly is a CNF, which is actually talked about here as well. Okay, so you need to read everything from resolution logic, hopefully including the completeness is not super duper important, but going through the example is important. Okay, so this is an example, and I will just kind of, since we have 2 more minutes, this is the original random Boolean expression. Okay, don't ask me why I use this particular one. It's just one of the random expressions that I come up with. So we look at this one, it has got negation, it's got disjunction, it's got implication, it's got conjunction, and things are nested in a nasty way, right? And then I go like, oh, guess what? This expression is actually the same as this expression here, which is a conjunction of disjunctions. And in each of the disjunction, it only involves either a variable by itself or the negation of a variable. It is a very specific format. So now the question is, can we really do this kind of transformation and convert any Boolean expression that is well formed into a conjunctive normal form? This is called a conjunctive normal form. So that is going to be the focus of the lecture on Wednesday. And that is the part that involves Boolean algebra. Okay, so we are going to talk about Boolean algebra on Wednesday. But I hope you guys are at least grasping the overall concept of what we are doing here. And with only 1 minute left, one more thing that is super duper important. The well-formed formula space of conjunctive normal form is finite. In other words, the haystack that we were talking about is not infinitely large anymore. Okay, is it large? Yeah, it can potentially be large, but it is finite. So that means if I want to trick you and say, hey, go find the needle in this haystack, but the needle actually does not exist, after 2 hours, you can come back to me and say, Tech, that needle is not in a haystack because I have exhaustively searched the entire haystack and come to the conclusion that this needle is not in a haystack. That is the big difference in terms of what we can and cannot do compared to the conventional way of using propositional logic. So we're going to take a look at that magic on Wednesday. Okay, but the understanding of this material really hinges on whether you guys at least follow up with all the reading of the material and kind of revising or reviewing your own notes that you take in the class. I will upload the recording as soon as I can. Okay, and I'll see you all on Wednesday.